Hi, grade 10s. So today we are going to continue with our study of thermodynamics, and that involves state and phase changes and what is occurring when a substance goes through a state and a phase change. So, what is a state change? This is from grade 8 science, even a little bit from grade 7 science, but a state change is when a substance changes from one state of matter to another. So you're going from solid, liquid to a gas, or gas to a liquid to a solid. We are going to concentrate, on 4 different kinds of state and phase changes. And the following 4 are, fusion, which is just a fancy word for freezing, but you might see that term pop up. So you need to know that fusion is liquid changing to a solid. Solid changing to a liquid is melting. Okay. Liquid changing to a gas is vaporization. You guys usually first learn it as evaporation. So we're going to talk about vaporization. And gas changing to a liquid is condensation. Okay, so these are the 4. Now, these 2 are obviously related to each other, and these 2 are obviously related to each other. We are not going to deal with solid to a gas sublimation. That's just not one of our main concentrations in this unit. So, when we're talking about phase change, we are actually dealing with energy because we need energy in order for phase change to occur. So the energy that is required, to complete a phase change of a solid to a liquid is actually the exact same amount, of energy. Ooh, got crazy. That is released when a liquid becomes a solid. So solid to a liquid or liquid to a solid, the amount of energy is the exact same. And that energy is either going to be released or absorbed depending on which way it is going. Okay, so energy is released when a substance freezes, so it's getting colder, and energy is required, or it seems like it's getting colder. We're going to talk about that in detail. And its energy is required or taken in when you are melting a substance. We do have to be careful when I'm talking about the word temperature, and that is a discussion piece that we are going to continue with. So, saying that, if you also look at the picture on the left-hand side of this pot, boiling some water, the exact same amount of energy is required to vaporize it. That is also released when a gas actually condenses from a gas to a liquid. Okay. So, thankfully, to make our lives a little bit easier, we're going to actually only be dealing with phase changes of water in this course. Water is the most abundant substance on this earth, so it is kind of a big deal. And because we're only dealing with water, you are going to be given some constants on your data table, which is on the back of your periodic table. And at the bottom, just like we were finding the constants for C, we're also going to find these 2 constants that we are going to use. I don't know what's happening with my pen today. For heat of fusion and heat of vaporization. Now, you are going to have to pick which one we use, just like we had to pick with specific heat capacity calculations. Now, this is where you need to understand that fusion and melting and vaporization and condensation and their relationship between the two of them. So if you are going from a solid to a liquid or a liquid to a solid, okay, in your questions, you will always use heat of fusion. If you were going to go from a liquid to a gas, vaporization, or back the other way, gas to liquid, you will use a H vap or H vaporization. And you will notice that you have your two different constants. Okay. And what those constants actually mean is basically how much energy, how many kilojoules of energy is required in order for that phase change to occur for 1 mole of water. So heat of fusion requires only 6.01 kilojoules for 1 mole of water to go from a liquid to a gas. Or sorry, we're going heat of fusion, solid to a liquid. Heat of vaporization requires a little more energy in order to go from a liquid to a gas, even though it's the same amount of water. So we have to pick these very carefully. Okay? So saying that, there are some key pieces on this. This is an important slide right here, so pay attention very closely, please. When a substance changes state, okay, all of the energy, I don't know what's happening in my thing today. All of the energy is going to go into or leave the substance, and it's going to be used to break or make bonds, depending on which way it's going. It is never, ever, ever going to actually increase or decrease the actual temperature. Okay, which sounds a little odd. But if you were to have, okay, a pot of water, excellent drawing skills with my pen today. Okay. There's my pot of water. And that water on a stove starts to boil. It doesn't matter if that boil is a low boil or a really high, vigorous, crazy boil. Believe it or not, that temperature that it is going to be at, no matter what, when it is boiling, is always going to be in perfect normal temperature, 100, perfect normal, standard, typical place, 100 degrees Celsius. If you were to stick a thermometer, and you actually want to try this at home, stick a thermometer in as a pot of boiling water. As soon as it starts boiling, it'll be 100, and it doesn't matter how high you crank your stove, as long as it is boiling, that temperature will remain the same. That temperature is not going to increase or decrease. Okay, the same goes for if an ice cube is melting. Until that ice is completely melted, it is going to be at that 0 degrees Celsius. Once that whole phase change is over, then your temperature could possibly change. So, formulas. You can find these two formulas on the back of your periodic table, your data table, okay, your data sheet. Q still is going to represent heat and energy, but the interesting case in this formula is different than our Q for MC delta T. The units for Q is equal to NH, or a phase change. We're actually dealing with kilojoules. Whoa. Okay. So We also have a different variable here. Q is equal to mc delta T had mass, where we actually have N, which is moles of a substance, and our unit for moles is MOL. This should sound familiar to you from our chemistry unit. And if you were to by chance not be given moles, we actually have to calculate it. And I will do a little reminder on how to do that. Okay. H is always given to you in constant, so you just have to look at the bottom of your data sheet and pick the right one. Are you picking HFuse or HVAP? And go from there. But really, really important, and something to maybe even put right on your data sheet, that Q has to be in kilojoules for this calculation. Okay. So what does this look like for questions? Maybe my pen will cooperate. So example 1, how much energy, so there is your Q. Okay. Q is your question mark. Is released, so it's actually going to tell you it's released in this situation at 2.50 moles. So this is your N. I really suggest that even if you don't put them on the side, you label things kind of as you go through the question. It does make your life a little easier. Notice I will always write the number as given to me in order for SIGDIGS to make sure I'm carrying through properly. And then it says when water vapor goes through condensation. Okay, so that means I'm going to end up using HVAP. So in order to find that, I look at my data table, my data sheet, and HVAP is 40.65 kilojoules per mole. All right, so now I have all my information pulled out of my question given. I'm going to write my formula. And then I'm going to show my work. So I'm looking for Q. N is 2.50 moles. I'm going to multiply this by 40.65 kilojoules per mole. Type it in my calculator, punch and play, and I should get Q is equal to 101.625. This unit is kilojoules. And if you actually look at the constant up here, it will remind you, because it is in kilojoules, that your Q is in kilojoules. So now we just have to deal with our significant digits. So I've got 3 in this, and I've got 4. This is a constant, so we are going to put still 4 SIGDIGs. So Q is equal to 101.6 kilojoules. And this energy is, oh my, that's not a box around it. We're going to ignore that. The energy is released when you have condensation occurring. Okay. Example 2. So, there we go. How much energy, so this is Q, is required to melt 50 grams? Now, note, pay attention to the units. This isn't moles, this is mass. Now, that does not mean you get to use your Q formula with the mass in it. We have to really notice and pay attention to our wording here. It says melting. So that means a phase change is occurring, which means you have to use Q is equal to NH. Okay. It does tell you a temperature, interestingly enough, but that just happens to be the temperature at which ice melts. And so we're going to actually ignore this 0 degrees. It does not imply that a temperature change is occurring. So Q is your question mark. N we don't actually know right now. And we are dealing with melting. So we're going to use H fuse or HFUS, which is on the bottom of our data sheet at 6.01 kilojoules per mole. Okay, now you're going to say, well, I have mass, but I don't have N. Can't I just put it in there? No. They are not exchangeable. But we do have this handy dandy formula right on our data sheet that is from our chemistry unit. N is equal to little m over big M. Okay. We are dealing with ice. So we're dealing with water. Okay. So we sometimes will have to do this little side mini step for these calculations. And what that means is we're going to take our mass and go 50.0 grams. Well, little refresher, how do you find molar mass? Well, water is H2O. That means there's 2 hydrogens, 1 oxygen. Oxygen is 16 molar mass. That's on our periodic table. And oxygen is 1.01. And we end up with a molar mass of water 18.02. Because this is the only really molar mass we use in our physics unit, because we're dealing with water so much, this would be a good molar mass just to memorize, 18.02 grams per mole. Or you can figure it out every time, but molar mass is 18.02 grams per mole. Mass divided by molar mass, and you should get 2.77 moles. So now we have all of our required information to complete the question. So Q formula is equal to N times H fuse. Q we don't know. N is 2.77 moles. We're going to multiply it by our constant, 6.01 kilojoules per mole. And once we type it in our calculator, we should get 16.6759. It's not pretty. Do not round or change your sig digs until the very, very end. I wrote down 2.77, but I actually used my full decimal that I calculated here, just so I didn't change any answers. So my full answer with significant digits should be 3 sig digs. Okay, so I have 3 here, H fuses 3, so 16.7 units for energy here is kilojoules. And because you are melting, okay, the energy is going to be absorbed. And that is it for examples. So a little just recap review. If you see a question, because you're going to get some of these specific heat capacity water questions mixed with phase change questions, you know how to pick between the two. Okay? So if you see melting, condensing, vaporization, or freezing or fusion, you are dealing with Q is equal to NH. Okay? Specific heat capacity, you will notice because of the formula, it is only dealing with temperature changes. Okay? So if there is a temperature change, you are going to use Q is equal to MC delta T. If there is a phase change, you're going to use Q is equal to NH. Okay? Do not let a temperature indication like 100 kind of throw you off in these types of questions, because during a phase change, no temperature change actually occurs. If you went and got a slushy or a Slurpee right now, that Slurpee has a combination of water and ice. If you were to stick a thermometer in it and stirred it around, that temperature that it would be at and would stay the same until all the ice completely 100% melted. Once that phase change, that melting was finished, then the temperature would actually start increasing because it was warming up, but not until that phase change occurs. Okay, so that's the difference between your two water problems that you are going to get. And that is, for the most part, the end of a little bit of thermodynamics and phase change and specific heat capacity with water problems. Once again, questions, ask away, pop into office hours. Okay, bye guys.